What's going on? All right, so yeah, today I wanted to look at some .NET stuff. I haven't done a stream on .NET malware ever, I think, so figured it was about time. Got a pretty good sample from Tony on our Discord that is a great beginner sample. So if those of you who are on here want to follow along or take a look at it yourself, let me just link our repo here. So on our GitHub, we have a community malware research repo that we post samples to and research and a bunch of other stuff for samples that we're currently looking at. So it's usually pretty up to date, and we just work on those samples together on our Discord. And it's a nice, fun project for us to do periodically. We'll usually find like an easy sample to look at and then, or like a more beginner sample, and then reverse engineer it and talk about how we're getting to our solutions, etc. So there's the GitHub there, and that's the DCRat sample that we'll be looking at today. So yeah, if you want to follow along, definitely download that sample. And then this particular sample had some interesting stuff to look at, so including some obfuscation, anti-analysis, et cetera, et cetera. So it's not just like a super basic .NET sample, but it's pretty straightforward and pretty beginner. But just to give you some background on DCRat, it's a pretty old malware family. So let's look at some background on that first. So let me hop over to my Linux VM. So probably do Malpedia. So again, this is pretty old, Dark Crystal Rat. It goes back to like 2019, I think the oldest article on Malpedia is. And it's a pretty classic .NET C# backdoor that allows pretty standard rat functionality. So here, I'll just link the Malpedia entry on that. Okay, cool. Yeah, so I opened that one that I provided in the repo, and we can see the .NET disassembly. So actually, I'll back up here. So this is a program called dnSpy, and this is probably the de facto standard tool for analyzing .NET assemblies. There is a current fork that is up to date called dnSpy X. So let me link that as well, just in case some of you are not familiar with dnSpy X. So there's dnSpy X. And this is probably what you want to be using instead of the Flare VM dnSpy that I'll be using today. But this is just an intro stream, so we don't have to use like the latest and greatest tools. But there is a version of dnSpy that comes with Flare VM that I'll be using today. So that's the one I have open here. And then we'll, if we hop into the assembly here, so how dnSpy works is basically it's made to look like an IDE. So that's what I have open here. And then I've opened the sample here, which has sample metadata. And in this instance, this .NET assembly is called tar4pro.pc2. So it's whatever the malware author had implemented for this here. So, and then if we right click on this assembly, we can do go to entry point. So you can click on go to entry point, and then this will take you to the entry point of the .NET assembly. So how .NET assemblies work, it's a little bit different than how normal portable executables work, because this is what's called a managed language or a managed framework. So the .NET framework effectively has the .NET code embedded within the binary, and then that's interpreted by a CLR runtime. And that runtime is embedded within a DLL that is then used to call the .NET framework that's installed on Windows machines. So the .NET framework is used for a whole bunch of things. So I believe most modern versions of Windows have the .NET framework installed by default, but you can kind of think of .NET assemblies as an equivalent to Java or any other bytecode interpreted intermediate language that is executed at runtime by an interpreter or like a virtual machine. So you can kind of think of it in that way. So this program dnSpy will take the intermediate language that is produced by the .NET compiler that Microsoft Visual Studio provides, and then it'll take that bytecode and then decompile it back into a .NET representation, or you can look at it in these different formats. So you can look at it in Visual Basic or the intermediate language opcodes themselves. So this is a lot harder to read than decompilation. So most of the time I'll use the decompilation C# view because it's very close to the original source code if it was indeed programmed in C#. So the reason that they have the Visual Basic representation is there is Visual Basic.NET, but I don't believe Visual Basic.NET is commonly used anymore, but you can lift these intermediate language opcodes into either a Visual Basic or C# representation. So that's why it provides those options. So if we look at the sample here, again, I just went to the entry point, and this is the entry point of the .NET assembly by right-clicking and clicking on Go to Entry Point. And then we have this main function here, and upon entering this main function, we have a number of different things that happen. So we have this settings.delay. So what's really nice about this interface that dnSpy provides is I can just click on these attributes. So these are just class public static strings in this instance. So it has a d_lay variable here that is set to the string 1. So if I go back here, we can see that this number 1 is converted to an integer using convert.toInt32. And then so it's basically just going to iterate over a single loop in this for loop. And then we have a thread.sleep. So this is going to sleep for this amount of, I can't remember if it's seconds or milliseconds. It's definitely not 1,000 seconds, but I think it's just 1 second, but let me double check. So I go back to my browser here. So the reason I have a Ubuntu window open in addition to my Windows machine is that other machine will probably be doing some dynamic analysis, etc. So I don't want to have an internet connected machine that I am doing dynamic analysis on. So that's why I have this like separate window here. Oh, thanks, bad code. It's milliseconds. Okay, so we don't even need to check the docs there. It's just 1,000 milliseconds, which is indeed a second. So we don't have to worry about that. And then if I go back to my Windows machine here, then after it sleeps, then it checks out the initialization settings here. And this is just a function call that does a whole bunch of different stuff. So in this function call, we have a bunch of more class variables that are initialized. And these are initialized using these other function calls. And as you can see, if you're familiar with cryptography, there is these calls to AES 256. So this is likely performing AES decryption here, especially since it's AES 256.decrypt. And then there is a number of settings that is decrypting in this step here. So, and the first thing that it does is it acquires this settings.key. So I'm just going to click on the settings.key here to go to this class variable. And then we can see that there's this base64 string that corresponds to this class variable key. So why this is important is the settings.key, once it's initialized, is then passed to this AES function that is used to decrypt all these other configuration items. So if I go into this settings.aes.decrypt, then we can see that this is a custom function that they have here. On the left-hand side here, it's really useful also in dnSpy when you navigate to a separate, say, class file, for example, that is within this namespace, then you have the namespace implementation for client.algorithm. So on the left-hand side here, it's pretty tiny for you guys. I couldn't actually get this font bigger. I don't know why, but this class lives under this client.algorithm namespace. And this is actually the implementation from the malware author themselves. So if we look down here, then this encrypt function, we want the decrypt function that we were looking at before. We have from base64 that is passed to decrypt, and then the string is acquired from that. And then if we go to this.decrypt, then there's this decryption implementation, and we have a memory stream that is initialized with the input byte array, and that byte array is used to, or that byte array memory stream is then passed to this hmac SHA call here that is used to acquire a 32-byte key. And this first array here, these are computed to be equal, and that's just establishing the message authentication code. I should just read the text there, and that's used to verify the authenticity of that key, I believe. So this should be a part of, okay, so it's reading the first 32 bytes into that array and then ensuring that those are equal. So it looks like they have some integrity built into the memory stream that they are indeed decrypting, which they use for the HMAC there. And then here they are creating a crypto stream. Oh, sorry, before we get to that, they're creating a 16-byte array here, and then they're reading I think it is the preceding 16 bytes, so dot read. So let's look at the dot read implementation. So like I said before, I wasn't sure if this was the actual malware author's crypto implementation or the actual library. So I clicked on the dot read implementation here. And then as you can see, this is actually within the .NET standard library. So depending on what you click, then you'll actually navigate to the .NET standard library there. So, and here we have the labeled parameters, which are very useful because of the metadata that's stored within the .NET assembly. And then we have the buffer, the offset, and the count. So this is reading okay, so this is indeed reading from the 0 offset. And then that is used as the initialization vector for the AES encryption. And then that is used to, let's see, where's the IV passed? Okay, generate IV, get resource. Okay, again, this is part of the crypto library. But the array is used to set the IV part of the AES crypto service provider, which is initialized up here. And then within that AES crypto service provider, this is quite important, so I'll just go over this. I know I kind of skipped ahead to the HMAC verification, but they set the key size as 256, the block size of 128, and then the cipher mode as CBC, which is the chaining block cipher mode, and then the padding mode is set to PKCS7. So these aspects are important if we want to decrypt the data that is being decrypted at runtime ourselves using Python or something like that, which we'll probably do. And then again, we have the key that is passed, and then that's used to initialize the AES crypto service provider. Okay, so TLDR, they're using this function to decrypt a given input with the global key and auth key that's used as this HMAC class variable. So I think that's constant throughout, right? Because they would initialize this A object or AES object. Let me check. Yeah, so they're just creating a single settings.eas key object per time that they're performing these decryption operations. So that's constant throughout the binary. So then this will be a global, I'm sure. Let's see, settings.key. And then are they reusing this? So what's also really nice in dnSpy is you can right click on these objects and then click analyze. And then they'll pull up all the locations in which they're used throughout the binary. So if I go to assign by and then read by, okay, then I can just see that it's only used in this function. So it's not a global like I thought, which is fine. But the setting class it doesn't matter. But yeah, so we have a whole bunch of different config options that are decrypted at runtime, and then they are used throughout the operation of this malware. So if I right click on the settings object, then click analyze, and this will be used a lot more, I'm sure. Used by, yeah, so it's like used in a whole bunch of different places or a whole bunch of different spots throughout the binary. So they're going to be using these settings class variables to do a whole bunch of different things. So before we get to that, we can probably go back here and then see what the next step is. So also the nice thing in dnSpy is I can use these little arrows up here to navigate backward and forward. Again, I know they're probably tiny for you guys, but very similar to an IDE. Hey Osiris, how's it going? Okay, so let's continue on. So that was the initialize settings function that decrypts all those values with AES. And then if you scroll down here, again, this is a really good beginner malware sample because they have every function nicely labeled for us. So it's not really too difficult to figure out exactly what these things are doing. So like run anti-analysis is a part of this class. And that's based on this settings Boolean that is initialized in our initialize settings function here. So if the anti-analysis is enabled by the configuration, then this run anti-analysis function is called. So if we look at that, if we look at the anti-analysis stuff they have here, so the first thing they call is VM by WIM temper. I haven't looked at this yet, but this is WMI objects. So this is Windows Management Instrumentation. This is like a large framework. I don't know if you'd call it a framework. We could probably figure out what the formal definition of WMI is. Let's see. But this is a really common anti-analysis technique because the WMI database is used to hold a bunch of different system information that's used by Microsoft Windows at runtime. So it's a set of extensions. Here, you can probably make this bigger. A set of extensions to the Windows driver model that provides an operating system interface through the instrumented components provide information and notification. The WMI is Microsoft's implementation of web-based enterprise management. So basically, it's just like a whole bunch of interfaces that can be used to interact with operating system components. And all they're using it for in this case is to query the amount of memory, I believe. So if we go back to our machine here, our Microsoft Windows machine, we can see that they're creating this management object searcher. Again, this is all part of the .NET framework. So if I go up here, you can see there's like system.management. And then I believe that that's what this is a part of, management object searcher. And then they're doing this WMI query. So select star from Win32 cache memory. So they're basically searching for the amount of cache memory, iterating over the objects. And then it looks like they are just ensuring that, or they're checking whether or not the number of cached memory objects is greater than 0, it looks like. And then if that if statement succeeds, so if it's 0, then they call this fail fast thing. So immediately terminates the process before reporting an error message. So basically just exits using that fail fast function there, their method. But yeah, I'm actually not sure. I haven't seen that anti-analysis trick before. It's kind of interesting. Maybe we could search like, yeah, I don't know at which point you would have those cached objects. I'd assume it's an anti-VM trick because maybe it's not done often in VMs, or maybe if the system just booted, it probably wouldn't have any cached objects. Okay, so let's keep going. So the fail fast thing is cool, and well, even both these are interesting. So that's, I think, the only anti-analysis trick they have. Looks like for that call at least. And then they have a mutex that's created. So this is often used to ensure that only a single instance of the application is running, or the malware is running. So that's probably what they're doing in that case. And then the settings.mutex value is used. So that's again initialized in that initial function that was called. So it's just a hard-coded mutex within the malware that's decrypted using AES. And then they're not using that fail fast thing anymore. For this exit, they're just doing environment.exit. So it looks like it's part of the standard library. And then converts to Boolean anti-process. So let's see, start block. I don't know what anti-process is. Anti-process.enable is true, and then start block thread. Let's see, they're creating a new thread. Okay, and it looks like they're enumerating processes here. And if they have matches for any of these, then they call this kill process. I don't think this would work for some of these, like the MSMP eng. This is part of Windows Defender. And then this MP CMD run, I believe, is also part of Windows Defender. So if these are privileged processes, I don't think it would be able to kill them. But common analysis tools like Task Manager, Process Hacker, etc. are also in this list. So it looks like they're just calling and the user access control setting.exe. I don't know why they would kill that. But so how this works is they would establish a process snapshot using create tool 32 snapshot, and then they iterate over each one of these entries using this do while loop here. And then if any of these matches occur, so if we go into this matches function, it looks like they just do like an ends with comparison, a string comparison invariant culture ignore case. Basically it's just doing a caseless match and then seeing if the process ends with that. So kind of cool. And then they use this process 32 next, which these are all Windows standard libraries. So this create tool help 32 snapshot. And then they're acquiring these from the Windows standard library down here. So they do a DLL import, and then they get the applicable Microsoft Windows API function from that here. So you can see them actually getting that there, which is cool. So they're using a mix of the .NET and Microsoft Windows Standard API for some of these operations here, it looks like. What else do we got here? So it looks like this kill thread is done separately from the main thread. And does this just run indefinitely? Because that'd be kind of interesting. It looks like it might just run indefinitely, which is kind of funny. So they'll basically just like try and kill those processes in a loop. We could probably test that dynamically if we want. But yeah, so they'll initialize a anti-process thread, and then that'll basically run in the background and try and kill these processes over and over and over again, which is pretty funny. They also have things like regedit and yeah, a few other interesting processes there. Okay, so let's see, BSOD. I don't know what this is for. I should probably decrypt these values so we have them, but let's do that in a second. Is admin. So it just does a Windows identity check for the current Windows identity. This is like the nice stuff about C#, right? Is you can have these like high level functions where you could just check if you're an administrator in this amount of code, which is really nice. So it checks if it's an admin, and then checks against this Boolean as part of this BSOD variable. And then it'll set it as a, let's see, process critical.set. Enter debug mode. What does this do? So it just sets the SE debug privilege for the current process. And then I don't know what this incrementing session ending thing does. RTL process is critical. RTL set process is critical. I actually don't know what this does, so let's check that. Again, this is a part of the Windows Standard API, so protecting your process with RTL set. Is it another undocumented feature of the Windows kernel? It is one of which do not have a kernel 32 equivalent. However, Microsoft has a good reason not to document this function. It should not be used in any application for any purpose whatsoever. I simply cannot imagine the circumstance where this function would actually become useful. Okay, so it looks like it just sets a system critical process status. So I don't know if that would change any behavior of like antivirus terminating it or anything like that, but this is interesting. I'll throw this in the chat too. Okay, there's that code project link if you guys want to check out that technique. I don't know. This is like really old. So this is from 2009. So I don't know if any of this is still relevant on like modern versions of Microsoft Windows. But when the critical status is set, termination or ending of the process in any way will cause a BSOD. So that's pretty cool. So I think that's why that config item is called BSOD, because they're checking if that's enabled in the config in order to set the critical process flag that would cause a BSOD if it was terminated. So that makes sense. That's pretty cool. And then, and they're only doing that. They're only setting that critical process flag if the process is running as administrator. So I assume that's needed for that. Install. So this is probably used for persistence across reboots. Let's double check that. So they're expanding the install folder environment variable, so app data, and then creating a file info object from that. And then they're using that, it looks like, to get processes. Okay, so they try and kill any files running from that directory already, which is kind of interesting. And then if the file is running as administrator, then it'll execute cmd with this base64 decoded string. So let's check what that is. So I'm just going to open up Cyberchef, and then I'm going to paste that string into Cyberchef and then base64 decode it. So I'll just use the from base64 recipe, and then it says basically it's a scheduled task that it's creating there. So let's see if I can modify this. So let's edit the method, and then let's just add a comment there. Oh, I thought that would add the comment, but let's see. It doesn't really matter, but we just know it's scheduling a, let's open up our little notes here. I'll just open up a Notepad++ on here for now. So it's creating a schedule task using the command. So like if you had an EDR or something, you could just obviously detect on this. It's just kind of sketchy. So yeah, it's just creating that task, and then that's going to execute on boot. Is that correct? Yeah, on logon. And then it's going to, looks like it's going to execute that file on startup, And then let's see here. That's only if it's running as administrator. If it's not administrator, then it'll add a registry key. So again, if I do our decode in Cyberchef with base64, then it's just adding a run key. So under software, Microsoft Windows current version run, then it's creating a run key with the file name there under app data. Is it actually writing it to app data though? And it looks like it's also deleting that file if it exists already. Okay, yeah, so here, this is where it's happening. So it creates a file stream and then it does a write. And then it looks like it's creating a little bat file that will start and then delete that file. And then it executes it. So again, it would be I think this get temp file name makes like a random looking file name. And then it would create that with a .bat extension under either the run key path or the scheduled task. So the other thing that is important to note here is it looks like they're creating a temporary path under that directory as well. So it'll be in a subdirectory, and then what else? It looks like the registry value itself is set to the current file name of the executing malware. You don't use backspace key in dnSpy instead of clicking. I don't know. Is that a hotkey? Backspace? Oh, that's cool. Thanks, Reroot, for that tip. But usually on stream, I try not to use hotkeys just so you guys can see what I'm doing, but it's still a good shout. Okay, so any questions about those things? Pretty straightforward. Again, this is super readable code. It's almost like we're reading. Source code, but we'll get to the crypto stuff in a second, and then it'll be a little bit more interesting. But before I do that, I just wanted to go over some of the initialization stuff here. So we have prevent sleep, which it looks like it sets an execution state for the thread. I don't know what this numeric value corresponds to. Maybe I can Google this. I really wish my VM would stop logging me out. Let's see. Yeah, I don't know. I don't really know how setting that thread change will actually prevent it from sleeping, but maybe we can figure that out. And then let's check maybe they don't want the main thread to sleep. Is that what that's for? Okay, and then the clear settings will do what? Let's see here. So, okay, so it creates a subkey, environment, win directory. I don't know why I would delete these. Do you guys know? MSC file and MS settings. Is that related to AMSI? That's weird. But it's deleting the entire tree. So I assume this goes through each subkey and then deletes the values. And then let's go to AMSI Bypass. Again, super readable function names to figure out what it's doing. So for those of you who are not aware, AMSI is a anti-malware scan interface on Microsoft Windows, and it's used by Microsoft compatible antivirus products to scan various things, including things like PowerShell and a number of different scripting interfaces on Microsoft Windows. And I think AMSI also does a whole bunch of other scanning techniques that are basically callbacks for those antivirus products. So more often than not, you'll have malware that's trying to patch those AMSI callbacks that provide information to the antivirus products. And that's what's happening here. So you have these bytes that are concatenated together. So if we were to concatenate those, it would just be like this plus this is a second line plus this, and of course the base64 encoded like everything else. And these just differ whether or not it's using this type of patch or this type of patch, as if the process is 64-bit. So it's using the int pointer size is equal to 4 to check that. So this is just like a very basic runtime check that checks if the int pointer value size is 4, which would be indicative that it's a 32-bit operating system or a 32-bit process. And if it was 8, then it would be 64-bit. So that's the data, checking the data type size for the pointer to an integer. And then if it is that, then it uses this patch function to patch these given bytes. And then it looks like it's doing, let's see. So I'll decode those AMSI patch bytes in a second, but let's see what these are. Text split to avoid detection. Yeah, I assume so. Arsenal Apen, but obviously not super sophisticated. So yeah, they're resolving the AMSI DLL here. So let's see if I can edit this method. And then this is going to be, that's the only place that's used, right? And then this is going to be the callback scan function thing, AMSI scan buffer. I always forget what that's called exactly, but so this is going to be the function that they're patching at runtime. So if I replace this with AMSI scan buffer, then that's the function they're resolving. Again, these are native Microsoft Windows APIs that they're resolving with get proc address to get that AMSI scan buffer function. And then they're doing a virtual allocation within the location of that function in memory. So when it does get proc address, basically it's going to find the location of AMSI scan buffer within the memory space of the running malware process. And then they're just patching that by doing virtual alloc x within that function, and then marshal.copy to copy the patch bytes into that location. So this is pretty standard patching stuff. Probably patching the first bytes in the function return 0. Yeah, exactly. Damok, how's it going? So if we want to check that to confirm what Damok said, we can just take either of those lines. So let's take this second one here, decode that in our little Cyberchef instance here, save this to disk. And then if I open that in IDA, for example, then we can confirm that. Where did I just save that? Let's see, is it on the desktop? Okay, I can't do it in the IDA free version, so I'm going to use Binja. I have IDA Pro, but it's just installed on my host, and I don't want to move that tiny file on my host all just for that. So let's open the file, and then we can see here that it's moving this return code into AX, and then it's returning. Let's see what this return code is. It's probably like failed to scan buffer or something. So if we go to AMSI result, then I don't know what this value is. Let's see. I just need the corresponding message, E invalid arg. So yeah, basically it's indicating that the AMSI context is invalid apparently. So that's all that patch is doing. So pretty much what Damok said. Oh, thanks, Arsenal Apen. You found it before me. So that's what they're doing there for the AMSI bypass. And then, so yeah, not super sophisticated. Basically, they're modifying the AMSI scan buffer function within the process space of the malware itself, but still pretty cool. And then let's go back here. Then it looks like they start doing some command and control stuff. So initialize client, let's go there. Oh, so they're just doing like straight socket connections. Okay, so they have a socket family that's created, or a socket structure that's created, or object in C#. And then they're doing a TCP socket. It looks like the send and receive buffer size is 51200. I don't know if there's any rhyme or reason for that. And then it looks like they have a paste bin option, and then they're splitting on the hosts. So it looks like the host can be comma separated, so they can have multiple C2 domains, it looks like. And then the TCP socket connects to that IP address. And then if it succeeds, so if the TCP client status is connected, then it'll break out of this for loop when it's iterating over each of those IPs, and it's acquiring the IP address. I kind of skipped ahead of that by using this get host addresses call. And this, again, this is a part of the standard library where it's essentially resolving the DNS address that's provided in the configuration there. And then once it connects, it looks like it establishes a web client. Oh no, sorry. So if pastebin is not null, then they create a web client, and then they'll download a string from the given pastebin address. So, okay, and then what else? So once the client is connected, they do a TLS or SSL stream verification. So it looks like there's an embedded certificate within that configuration as well. And then they set a whole bunch of different client socket information that apparently has the ability to speak TLS, which is pretty cool. And then once they're connected, there's probably a whole bunch of comm stuff that it can do. It can do some reconnection stuff. Okay, so once it's connected, I assume it calls read server data. And the read server data, let's see. Okay, so they read that within a thread, and they do a .start function. And are they doing that with the given buffer? So they're literally just acquiring and executing the buffer in memory. Is that all that's doing? Let's see. Keep alive packet. Okay, so they have custom packets, it looks like, for a ping and a pong. And then they have the ability to provide plugins, send plugin, hashes, invoke. Okay, so this looks like it actually loads the plugin when it's provided as a C# object, which is essentially a .NET assembly. They have received. Okay, so when they get a packet, forced object path, message.pack, message. Let's see what this is. Message pack. So I don't know why they implemented their own like custom protocol on top of TCP, but it's kind of interesting. It looks like they have a mechanism to switch from network byte order. Let's see what, and then the ability to parse given data types as well. So this is actually kind of complicated. But yeah, not entirely sure why they decided to implement their own protocol on top of the TCP stack. Like, is this a standard protocol, or did this just get like ripped off from one rat and it's been like used by a million others? Okay, so async.rat had it first. So we can look at some of the embedded capabilities in addition to the plugin loading stuff. So the anti-process stuff, we looked at that already. Anti-analysis, we looked at that. Camera. So it looks like it's looking for CLS IDs that have the video input device category. And then it'll filter on those monikers. So I guess it'll just look for video devices and then read from it probably. This isn't super important because I'm more interested in the malicious functionality, but basically it allows to read from a given camera CLS ID. But this is all like component object model stuff. Yeah. And then it reads from that given interface once it's found, this COM interface. Okay, so then the other capabilities, hardware ID generation. So this is probably used to identify the given infected machine. So let's see where this is used. So I can right click and then go to analyze, and then again, it'll be in the initialization settings. So this is called in this step. So I missed that earlier. So it's good that we checked. And they're basically concatenating all these environment variables together, it looks like. So they're doing processor count, username, machine name, OS version, and then the drive info path. So with the drive within the system directory, and then getting the entire disk size. And they're MD5ing that to get a unique identifier, and then they're just getting the hex representation of that using this toString call here for each byte within the array that's computed using MD5. So that's all that is. And then they're sending the enumerated system information here. So again, this is probably called in that initialization function that I missed earlier. Okay, so this is when the C2 stuff was happening. This is when this is done. But basically this will create a client info packet. It'll get the hardware ID that we just looked at, the username, the operating system. It has a Boolean indicating whether or not the system has a camera, the current process, the version, whether or not they're administrator, performance, get active window title. I don't know why that's called performance, but it's getting the current foreground window. The pastebin settings, antivirus. So let's look at the antivirus stuff. This is also very common. So they'll basically use the WMI interface that I was talking about earlier, and then they'll use that to query the antivirus products using WMI, and then they get the display name, and then they concatenate all those together using semicolons. And then they get file information. So I think that's the persistence path, the last write time. for the executable path. It's kind of cool that you can do it that way. And then the group, so this is probably the group that the computer's been set into. And then it's encoded into bytes. Let's see what else is. So I think we got most of these. So nothing crazy or like earth-shattering. But the thing I wanted to do next is see if we could just extract those configuration items automatically and then decrypt them. So I've done some .NET stuff in the past, .NET automation, but it's a little bit harder than some of the binary stuff because usually I use things like Binary Ninja or IDA for extracting information, but that's not always possible with these .NET assemblies because they have, again, that intermediate level representation that is within the custom format that's interpreted by the .NET CLR at runtime, or the common language runtime. So in order to parse these .NET files, you can do a couple of different things. There's dnlib, which is, can you do conditional breakpoints? Yeah, I think you can do conditional breakpoints in dnSpy. Let's see, maybe not from this interface, but there's like a command line interface that you can use. I'm actually not sure. That's a good question though. There's like a whole REPL, but let me check. You may maybe add one on access. Yeah, I think when you do set a breakpoint, let's check here. So if I go to the entry point, so I know you can set a breakpoint by clicking there like that. Settings. Yeah, conditional expression. So then you can like have this evaluation. Condition is true. And then I don't know what you can provide as the conditional expression, but that's how you would set a conditional breakpoint. You can have a specified hit count, so I assume you only want it to only break if you hit that specific hit count. So if it's hit like 5 times, then it'll actually break. Then it looks like you can do a filter on a specified syntax as well, and then do a log, which is kind of cool. Oh yeah, I can do the settings object to be decrypted that way for sure. We can do, yeah. Why don't we do that first? Before I jump ahead to doing it programmatically. So if we go to our initialize settings here, and then I can set a breakpoint here on the X509 certificate or the verify hash, whatever. Then we can hit start. Let me just make sure I don't have any, I don't think it has any file infector functionality, but I just want to make sure my shares weren't mounted. And then we hit start here. And then here we can say break on the entry point. So I can hit OK. And then we don't have a valid extension right now just because the file doesn't have an extension at all, but I'm going to hit yes. That could be like an anti-analysis trick. And then so we get a break on the initial function here. And I can actually just do a step over. So it'll sleep for that 1 second, enter this for loop again, and then it checks if these settings are initialized. And then I hit step over here, but we hit that breakpoint. And then within this function, I should be able to see those globals, public members, show tokens. Is it because these aren't locals? Analyzer, let's see if I can clear these. I should definitely be able to see those values. I can't remember how to see globals in dnSpy. Let's see. Do you guys know? You just set breakpoints internally. Hey Shadow EXE, what's going on? Try adding this to watch. It's on the Assembly Explorer, right? No, that's on the left-hand side. That's what that's called. Time to add a little D4 dot. No, I don't think we need to use that either. Yeah, I know what rerout's saying. Let's see. Okay, here we go. I think this is what I want. Autos, locals, watch. Oh, I see what you're saying. What does this do though? Try to step in. But I already like passed over, hold on. Modules, threads, processes, memory, disassembly. Like what do these watches do? Watch 1. Settings is a type. Does not have a valid. Oh, can I do like settings.key? Yeah, there we go. Nice. Good shout. But why isn't it decrypted? Or no, that is the key that's decrypted, isn't it? So if I do, I know that's really tiny for you guys, but if I do like settings dot hosts, Yeah, then these are the C2s. Nice. Cool. Yeah, but that was correct. Nice. I didn't even know you could do that. So see, I'm learning with you guys. Okay, so yeah, so if we really wanted to, we could add like every single decrypted config entry here and then get it that way. But since we might want to like do this on multiple files, I wanted to see if we could extract these values programmatically. So I wanted to see if we could use a library for that. So let's see if I can pull that up. So the first one that I think a lot of people use is dnlib, which is I think used for dnSpy. So if we look at reads and writes.NET assemblies, and then basically you can use this to access various values within the .NET assembly using .NET. But the other project I wanted to look at was the dncil from Mandiant, which basically lets you interface with dnlib through Python, which I thought we could look at for extracting values from, and then dnfile as well, which I believe dncil is dependent on. But I think we use dnfile to extract some of those metadata stream lists, which contain the AES key, etc. So I think we can try a few different methods to extract that programmatically, but maybe I didn't install it yet. But yeah, let's just install. So I kind of want to do it in Python just because my C# skills are really bad compared to my Python skills. Any questions about any of the stuff I did, by the way? dnlib for config extraction. Yeah, basically. My only pain point was while using Cyberchef, I couldn't derive the AES key from that key phrase, wasted like 4 hours. Yeah, so that's what I want to look at doing. But there's a custom encryption thing there. No, it's all standard stuff, I think. So if we go back to the decryption algorithm, so using that key, it calls decrypt, converts it to a memory stream, and then initializes a AES crypto service provider. So it uses, again, the CBC cipher mode, the padding mode of PKCS7, so that might be a pain to implement depending on our libraries. And then it sets the key, and then it just uses the HMAC with that auth key value to verify that the key is indeed correct for the key integrity, and then it uses the first 16 bytes to get the initialization vector, and then the rest of the key is the AES key. So if I go back here, so let's copy out this AES key. So we can probably do a test run in Cyberchef just to make sure that we understand the encryption correctly. So if I do AES decrypt, the key is going to be, let me just open Python here. I remember somehow detecting the method using X509 certificate. Okay. That's not the AES key, Josh. Oh. Yeah, it is. Is it not? The dot key? Oh, let me go back to the settings here. Yeah. Settings.key. This is used to initialize the AES object. Or is this what you were doing yesterday and it took you forever because you're trying to derive the bytes? So it derives it from a salt. Maybe we can't do this in, yeah. I don't know if we can do this in Cyberchef. I don't even know what this RFC is. Let's check that. Search this in DuckDuckGo. Oh, that's the PBKDF2 key derivation function. So do we have that in Cyberchef? Yeah, thanks Demock. Okay, so let's derive the key first. Let's get rid of some of these guys for now. And then the passphrase is going to be the master key, which is that value, this guy, without quotes. And then the salt will be this one, Latin 1 for each of these. And then the derivation is being passed what? Is it the number of iterations or something? Yeah. So if we go back to here, then iterations will be, was it 50,000 or 5,000? 50,000, I'll just copy paste it. And then the key size is 128. This guy is how big? So it's 256. So it's 32 bytes and therefore 256-bit key size. Okay, and then, so I think that's right. look for the class with the AES crypto provider so we can look at the salt. Yeah, so this AES256 object is setting these get bytes, the key and the auth key. So the key is going to be the first 32 bytes. Oh, no, wait, sorry. Derived bytes. I think we just have to worry about the first 32 bytes, right? Because this should be, do you think each time this is called, it's going to modify the state of this object? I don't think we need the auth key for anything. So if I look at the location this is used, no, it's not. Okay, I'll trust you read it. Okay, so the padding we need as well, and that's using that as the HMAC. The auth key is just used for the HMAC. So the first 32 bytes is going to be the first 32 bytes of every memory stream is going to be the SHA-256 HMAC for the data, it looks like. And then the next is going to be the IV. And then the rest is going to be the ciphertext. Okay, so let's use this. So this is going to be, the first 32 bytes is the key, right? So let's get that. And then let's just turn that off for now. So that'll be the key. And then the IV is going to be the first 16 bytes of any of these given values. So if we go back to the config, let's grab one of those to test with. Okay. And then let's use like the host one that we already know the value of. So then we'll copy out this string and let's just make a new Cyberchef window to make this easier on me with the X509 cert. I think the X509 cert is just used for the C2 comms. Okay, so let's do 2 hex spaced. And then I'm just going to get the first 16 bytes of this. No, that's hex, so we want the 32. Wait, shit. So that means the key is wrong too. Hold on, sorry. Hex is confusing. So we actually, because this is 32 bytes, so we actually want this to be 64, right? Which is the entire thing. And then this will be hex as the key. Okay, it's already set to that. And this will be 32. And then the IV. Okay. And then let's get this is all Python byte slice stuff, but the input. Okay. I don't know. Oh, because the HMAC. So how big was the HMAC again? Anyways, that worked. So this is all this crap at the beginning is the SHA-256 HMAC. So yeah, so we understand all the crypto correctly, right? Cool, huh? So should we write Python to extract these and decrypt them? Yeah, exactly, demock. So if we want to visualize this, it'll be something like HMAC SHA-256, then the IV, then the ciphertext. Then this will be like it's like that. Okay, and then the next thing I'm going to do is programmatically extract each of those values, and then we can use that to decrypt the config items automatically. So I think dn file can be used to do that. So let's look at that. If I can skip over to my VM there. Okay, before I do that, I'm just going to run to the washroom because I've been drinking a bunch of water. So for those of you who are new here, I do malware analysis training. So that's what enables me to do these streams for free and put out a bunch of content on YouTube and do all these open source projects and stuff. So if you want to check us out, you can check out our training here. So invokere.com, and I'll just throw that in the chat. And I'm just going to play a little commercial for our course here while I run to the washroom, and then I'll be right back and we can decrypt all these values with Python automatically. So I'm just going to do that and then I'll be right back. Hey everyone, my name is Joshua Reynolds and welcome to the Invoke RE Introduction to Malware Binary Triage course. Throughout this course, you will learn to triage and reverse engineer malware binaries using a number of proven techniques. These include static analysis, which is the concept of analyzing malware at rest, and dynamic analysis, which is the concept of analyzing malware as it executes. We will also be analyzing network protocols used in malware command and control communications, malware obfuscation, packers and how to unpack them, process injection, how to write effective Yara rules to detect malware variants, and how to compare malware samples at a binary level. This course consists of 11 modules, each containing lectures and practical labs to apply knowledge that you have gained as you complete the course. We provide both video and written materials, so no matter what your learning style is, you can complete the course successfully. Thank you for checking out the course, and we look forward to teaching you. All right. Whoa. Hey, thanks for the raid, Zed Shah. How's everybody doing? Go to the bathroom and then get 40 raiders. That's pretty rad. Okay, so for everybody who just joined, we're looking at doing some malware analysis today. So we're doing this .NET remote access Trojan called DCRat, which is written in C#. And basically what we did up until this point, I'll show you just real quick. Hey, Dank Mullet, how's it going? Thanks for joining. Let's see here. So yeah, just to give some background, my name's Josh. I do malware analysis on the Invoke RE stream here. And we're just looking at this piece of malware with this program called dnSpy. And basically it will decompile or recover the source code for a given .NET assembly or C#. Cool. Yeah, thanks for the raid again, Zed Shah. This is super cool. So what we did so far was we basically looked at all the functionality in this piece of malware. And then we've just been working on the encryption routine that is used in this malware to hide some of its functionality. So I use this program called Cyberchef to test our reverse engineering of the encryption that's used in this malware. And the encryption in this malware is basically used to hide the configuration items within the malware so they can't be extracted easily by reverse engineers such as ourselves. So basically this piece of malware is using this encryption algorithm called AES, which is the advanced encryption standard, and then it's using this embedded key to decrypt the configuration items it uses to contact the malware operator. So that's all we decrypted here was the configuration item used to get the website that's used to contact the website that's controlled by the malware operator. So that's what I did there. So if we want to look at, so let's check out Zed Shah's channel, because I'm not sure what they do, because we should definitely give them a follow. So let's do twitch.tv Zed Shah. Since they said they had to raid and run, we can still check out their channel. And it looks like they do coding streams, which is sweet. So everybody go shoot Zed Shah a follow there. And it looks like they're an author of various programming books, painter of stuff, and a creator of weird art games. Nice. That's super cool. So thanks again for the raid. That's super nice of you. So if we get back to the stuff we were working on here, config 338, why not just edit the malware, add the decryption logging, remove the RC part. So we could definitely do that, but say we wanted to decrypt the configurations for a bunch of different malware samples from this malware family, then we can use the method that I'm going to use now to do that. Does that make sense? Config 338. Hopefully that makes sense. So to do that, I'm just going to show you the program or the library that I'm going to do that with. So if we go back to dn file here, so this Python library basically lets us read those .NET binaries and parse out their streams in order to derive information. And the .NET stream table, so within the metadata tables, contains the strings that we need to get that AES key that we need to decrypt the remaining values. So if we look at some of the examples here, you can basically use this to load a .NET file and then parse all the metadata streams in order to acquire them. So let's do that and see if we can just basically take a shortcut to get ourselves most of the way there with just this dn file rather than parsing the actual .NET assembly instructions, because that would be a lot faster. So I'm going to do that. So let's set up a virtual environment within this DCRat directory. So I'm just going to do python3-m venv, and then I'll just do venv. So this is just going to make a virtual environment. And then I'm just going to install this dn file project here. So hopefully it's compatible with my version of Python. In order to initialize that virtual environment, I'm just going to do source venv activate, or bin activate rather. And then if I do which Python, then this is our Python instance within that virtual environment that I just created. And this just makes it a little bit tidier, so I'm not creating or adding the Python library to my global setup for my Python on this virtual machine here. So it's just a little bit cleaner. So I can do pip install dn file to get that. And then if I do Python import dn file, then we can see it's working. So let's just try loading the piece of malware with this dn file line here. And I'm just going to get the file here. So if I do file on this, we can see it's a PE32 mono.NET assembly. So this is the DCRat sample that I just had open in dnSpy. And then Dankalot, off topic, thank you for showing me Cyberchef. Totally a tool that I will use from time to time. Yeah, no problem. Definitely a really good tool. And it's just really easy and fast for calling various transformation methods on a given piece of data. And because of those, settings might be copy pasted across async.rat. That would catch more than just DCRat. Yeah, exactly. Config 338 for sure. Okay, so let's load this file. So I'm just going to bring that back into the foreground here. And then we have the PE loaded here, and it's a dn file PE object. And then say we wanted to parse those metadata structures. I'm basically just going to copy paste here because I am very new to this library, but that's okay. Then we can see that there's a whole bunch of metadata attributes here that we can access from this pe.net.struct. If I tab here, then we can see all of those. And then I think the ones we want are .metadata tables. So the number of metadata tables, let's see here. Entry.data. Basically, I just want the strings table. So if we go back to our Microsoft Windows, you'll be able to see here that there's actually these parsed tables in our .NET Assembly Explorer on the left-hand side here. So if I go to, let's see, type reference, no, that's not what we want. I think it's under PE. Yeah, so we have these stored streams, and then under this tilde one that defines the tables, I think we should have all of our strings here. So these are basically the values that we want to parse in order to get all of the strings that are used throughout the binary, but there might be a better way to get these quickly. So type references, X509 certificate, let's see here. I think these are all the objects that are imported for type references. Let's see here. Can I just get them from this string storage stream? I think that's only providing the offset. Member reference, download string. So basically these metadata tables provide the offsets in which the data resides within the .NET assembly. And this is what's used by the binary at runtime in order to resolve those. And then dnSpy is using these values within these metadata tables in order to reconstruct the binary. So if I go to those configuration items, for example, let's see, where is it? Let's just go to our entry point. That was easier to find there. And go to our initialization settings, then we should be able to see these guys, settings.config. And then we can see this token is number 7 within the field table stream. So this is what I want to find automatically with those values, is if we can just find the key field, then we can find the AES key automatically. So, okay, so if we go back here, I think I should be able to just access these stored the stored stream 0, but let's see. Let me hop into my other virtual machine if I can, and then we'll get the entry point token to RVA, flags, metadata size. I might need to just look this up rather than trying to go through the structs myself. dn resource, our data entries, let's see, entry.data, number of tables, so dnfile.stream. Here, let me see, and the p.metafile.stream list. Let's try this. Print s. Okay, and then we have the user string heap, the strings heap. Let's see. So that's what I couldn't tell, is if this was a part of the tables stream. So I don't know if it's a one-to-one mapping, like what's in dnSpy to what we can access using this library. But let's see what we can do with these tables based on number of tables, tables list, s.tables list. Okay, field module def. Okay, so it's in here. So it looks like the metadata tables is what we want. So if we have the metadata tables list, the stream list here, and access the first one, then this is a metadata tables object. And then let's see here. This is a lot more complicated than I thought it was gonna be. Tables. Okay. And then we want the, yeah, maybe I'll just check out if there's an example for this. Stupid question, but do you think it's possible to create malware that also uses vulnerabilities in .NET disassembly tool so that basically if someone tries to reverse engineer the binary, they'll also get infected without running the malware? Yes, totally. That's definitely a possibility. Maybe less so in the .NET interpreter like we were looking at, but the other tools like Binary Ninja or IDA or Ghidra definitely have, I wouldn't say they definitely have vulnerabilities, but they're very complex parsers that are written in languages like C and C++, so it's definitely a possibility. Dank Molot. So let's see if I can get an example of the field here. Because even if I get the correct stream and I get these keys and offsets, then it's probably going to be a little bit harder to access the data than I think here. So let's see, we can do, there might be an example in dncil. So this is actually getting the instructions, but I just want to see if there's an example in here. cal from bytes, cal from dn file. Can we get through the address of the table stream? We could retrieve VIL and dnSpy. Yeah, basically I'm just trying to do that programmatically with this dn file library, but it's a little bit more complicated than I thought. So maybe they have more examples here. Tests. Okay, they do have an examples directory, so let's check that out. dn strings, here we go. Okay, so we have, yeah, this would have taken me a million years. See how it's parsing the user defined heap strings? So dnfile.streams user string heap is equal to that given heap, and then basically it'll get the size, and then uses dn.getData at the relative virtual address to get each byte. Damn, yeah, that's way more complicated than I thought. So at least we have this example we can leverage to extract the strings for us. So I'm just going to grab this, and then we'll do that. Okay. And then dn get strings 791. And then let's see if there's the key in here. Yeah, it's one of these. So can we get the, I guess we don't want to depend on the fact that it's probably called key, right? In every single sample. So we can do, let's see what base64 it is. But there should be a corresponding field name that we can key off of. But I do know the string data is stored separately than the field names like I was looking at in dnSpy, so that might be a problem. So dnnet metadata streams. Yeah, we might not have the ability to map those back super easily, but what I can probably do is figure out a way to, or we can probably just key off of the, let's see here. So if I go back, so we have each of the fields. Yeah, so these are stored in separate tables. So I think that's probably why it might be a little bit more difficult. I'm sure there's a way to do it. It's just me not knowing. There being .NET malware exploiting reflector flaw. So you launched the Rickroll video. Nice. Yeah, that's definitely a nice Rickroll. So this YZ is going to be the key. I just wanted to see if these would be in any given order that we could key off of. So if we have YZ, then the X509 cert, what's the H6B one? I actually don't know what that larger base 64 is used for. Let's see. So I can go to the same stream here. So this US thing, go to MD table. Yeah, this wants a specified row. So it just provides the offset. Okay, so let's see. You can use a reflector to interface with JS, HTML somehow. Oh, that's interesting. Yeah, I didn't even know you could do that. Okay, so let me get back to our data here. So like, I think I can probably just key off of the fact that it would be a certain size, but it's kind of crappy. But maybe for the sake of the stream, I know there is config extractors for DCRat that are in AssemblyLine. So maybe we can do our own implementation and then look at what other folks have done. So why don't we do that? And then there's probably a better way. But I do want to get these decrypted automatically. Master key cannot be null or empty. Yeah, I don't think there's any given rhyme or reason to the length of these. So this is going to be, I guess I can, yeah, let's do this programmatically and then I can figure out what this value is because I'm interested. So this is going to be the key and then this decoded. So we can look for all the base 64 strings and then do it that way. So let me do that. Okay, show strings. Then we're going to return these, right? Offset, print item.value. So I want to append these to an array that I'm going to return from this function. And then value. And then for each of these array values, so I'll have the resulting array here, or our string. Then we'll have the, just going to import base64 here. And then we're just going to base64 decode R. And this is probably going to throw an exception when they're not in the correct format, but let's just double check that it will. It does not. So R to append, not defined. Did I screw that up? R string. For R and R string, none type is iterable. We want to return that. Okay, and then in each instance that we have incorrect padding, we just don't want to care about that. So we'll just do a try catch block for that. We could try and filter out non-base64 stuff, but pass. And then we basically want like a small heuristic for the key, but I think the key is going to be a specific size. So I don't think it has to be because it's using that derivation function. But let's just assume it's going to be 32 bytes for the sake of the stream. And then we can test that against other samples. So if it succeeds, right? So then we're going to have our length R is 32. Then we're going to return, or just have our key is equal to R and then break. Okay, and let's just make sure that works. Okay, and then let's get rid of this print. And then we'll say key, the AES key is that. Okay. And let's decode it. So we'll do decode as ASCII like that. And then we're going to do all of our crypto stuff as well. So probably going to need, I don't know what the best AES libraries are to use. Thank you for a welcome stream. Good luck with reverse engineering. All right, sounds good, Dank Molot. Have a good sleep. It was basically injection of JavaScript window.open. So which program was that in? Across 2 hours with 35 people alive. Nice. Yeah. Thanks everybody for sticking around. I really appreciate it. Okay, so then the next thing I'm going to do is decrypt those values. So we need, if we go back to our Cyberchef here, then we need a few things, right? We need the key derivation PBK df2 thing. So let's get that. Python. Okay, so let's do hashlib. And does hashlib ship with Python? It does too. Cool. Okay, so let's use that. So we'll do import hashlib, and then we're going to use that guy to derive our given key here. So let's look at, so hashlib.hmac here. Basically, we're just like translating our Cyberchef into Python code now. So since we verified all those crypto operations before, I'm a dead, but in my RAID. Okay, so we'll do hmac hash is equal to that, and then does it get, what does it take as hash name? Was it SHA-1? Yeah, SHA-1. So we'll have, I don't know if it's a string, but we'll see. Password will be our key. I just don't know. I don't know why it's not giving me the, oh, it is bytes. Okay, cool. Okay, so then we have SHA-1, our key. So we actually don't want to decode this as ASCII. So for key. And then our salt was another string. So we need to get our salt. And let's see. I know it was in this list, so we got to print those again. Where was it? I know it's here. I don't think it was encoded, but I could be misremembering. Let's see in the sample. So I'm just going to go back to the initialization function here and then the decrypt. So this AES-256 key, I think this had the salt. Yeah, this DCRat. I like how it has DCRat in the salt. Let's Google this. Yeah. Ooh, there's a Cyberchef recipe, like what we were doing. That's cool. So like, is that salt going to be constant? I don't know. We can just extract it because it's going to be 16 bytes, I believe. So let's see. It should be in here. Hope so. Anyways, yeah. And then this is 16 bytes, right? 17 bytes. I guess we could like. That kind of sucks. Okay, maybe we'll just have a fixed salt for now, because it looks like that's in the other config extractors, and then we'll see what the better way is to do this after this, because I just want to get the value decryption working, and then we can move on to making this better. So let's set that there, and then we're gonna be, oh wait, I think that's all that is. Yeah, reroute. Okay, cool. And then we'll do hashlib, let's see, 500,000 application specific above our app iterators. Why is this underscore like that? Do you like iterations? So let's do 500,000 like that. Let's see if that works. All right. And then let's print the hmac hash, and it should match what we had in Cyberchef. Now we need to get rid of this grep. Okay, A8FC, is that what we had in Cyberchef? Salt pass raise D06. Is it 50,000, not 500,000? Is that what I screwed up? 50,000. Okay, cool. That's it. Yeah, thanks. Thanks, reroute. Okay, so we're almost there. Then we need, what else do we need? So we have the hmac. So the key, derived key is hmac. That's just the full thing anyways, right? So now we need an AES library. So we'll get that, but we'll do bin ASCII unhexify hmac hash. So we'll do derived key. Okay. And then, yeah, we need the IV, which is going to be from each of our successful base64 decodes. So we'll do like that. And then we'll have the, we don't want that to break anymore. B64 decoded dot append, and then we'll have the R here. RB. Nice. You can call me JMag on stream, that's okay. Not none type. If length RB. What's it complaining about now? Oops. hmac hash non-hexadecimal digit found. Let's print that out. Oh, it's not even in hex, because I was doing .hex before, so we don't actually need to do that. All right, so let's do that. Okay, so let's get the AES library so then we can decrypt this, and then we'll implement the IV stuff too. So AES Python CBC. We just need Do we need PyCryptoDome for this? I guess we'll use PyCryptoDome. It's probably the easiest. So I'm just going to grab that by doing, I just want to install it with pip. How do I install it? Oh, here we go. Okay, and then we're going to be doing their AES example. So we'll do from crypto.cipher. I know this is tiny for you guys, but I'm just copying this from the docs, so it's not a big deal. And then we'll do import AES. And then same thing here. I'm just going to grab the AES.new, and it'll be CBC for the mode. And then do we need to specify the IV elsewhere or what? Nonce is equal to that. And then the nonce is going to be our IV, I think. So it'll be for ciphertext in B64 decoded. Then we're going to do cipher. So it's going to be, what was it again? If I go back to the IV was just the first 16 bytes, is it not? Do you guys remember? Were you paying attention? Yeah. So then we'll have the nonce being CT16, incorrect AES length 20 bytes. Shouldn't this have been, let's see, SHA-1 key size in our HMAC? Shouldn't this have been the SHA-1 would be 32 bytes, or is SHA-1 20 bytes? Yeah, it is. So how are we getting the correct key size? Am I crazy? So why was this different size? SHA-1 hashing function, D064. Okay, that's wrong. How do I change the key output size for the hash lib? Maybe I need PyCryptoDome. Oh, DK length probably. Is the length of the derived key in bytes. Okay, cool. So that needs to be longer. Unknown parameters for CBC nonce. Okay, so that's not that. Okay, so that's right. And then how do I specify the nonce for AES mode CBC in PyCryptoDome? Thank God they have good docs. Okay, AES mode CBC, that's what we did. And then ciphertext bytes encrypt. Okay, and then result decryption is what I want. Unpad. Let's see. Okay, it's just cipher.decrypt. Okay, so we just provide the IV as a parameter. So we want this to be CT16. Okay, and then in some instances, we're not going to have an actual valid. So it needs to be basically the ciphertext that I'm assuming ciphertext is when base64 decodes properly, which isn't like 100% correct, because sometimes it's going to be base64 that's not actually base64 and contains our ciphertext, or it's going to be some of the other strings. So I just need to make sure it's greater than 16, so it has an IV, but it'll be the HMAC plus 16, so it'll be 16 plus 32, like this. And then it'll be cipher.decrypt, cipher.decrypt, and then we're just providing the ciphertext, right? So this will be CT16 onward, that'll be PT, and then our plain text will be without the HMAX, so we'll do plain text print PT 32, or wait, so it'll be 16 plus 32. So that'll be this salt plus the IV, sorry, not the salt, the IV plus the HMAC. Okay, let's see here. Oh, I think I screwed up the HMAC calculation. That should be right. Okay, let's see. There we go. Oh, wait, no, maybe not. Data must be padded to 16 byte boundary in CBC mode. I might need to adjust the padding calculation. So let's do unpad like they had here, but that should happen first. Like, is it just dying on the first one? Is that the problem? 16, we're so close. We'll do print CT. Okay, it's just dying there. Okay, it's the HMAC. Okay, and then once it's decrypted, we can get rid of the HMAC. Okay, It's not an encrypted string, 51 the length. Yeah, that's what I was trying to get rid of demock. Okay, so I don't know how to get rid of this padding. It's just unpad. And then it'll be AES block size. Unpad, so we need to import that from here. So basically, it's working. It just needs to be cleaned up. Cool. Look at that. Great success. So now I just need to skip over the stuff that's not padded correctly. Not sure how, but I was able to decode all those strings by using the IV. Oh, is the IV constant? That could be. It could be an insecure IV. Yeah, exactly what Demock said. Okay, so I think we can just try. Okay, so these are all the config items. So that's the mutex, the port, the C2 address, the version, that false is. This is probably the certificate. Let's see. Let's open another Cyberchef over here. Yeah, it's definitely the certificate, I think. Hold on, let me try this again. Yeah, it looks like it's the cert. Can we do a hex dump? Yeah, this is definitely the X519 certificate. Cool. So yeah, just to summarize, we extracted the AES key and then decrypted all the configuration items programmatically with this library. Where was it? I must have closed it, but with here, dn file. So if I open dn file again. So yeah, pretty cool. So yeah, if we really wanted to, then we could try this against other DCRat samples to extract that data. What else did you guys want to do? That's kind of all I wanted to do on the stream today. Unless any of y'all had any ideas. We can probably see if this works against other DCRat samples. Okay, cool. Yeah, I'll do that in 2 seconds. I'm just gonna run to the washroom and I'm just gonna run that commercial one more time. So for those of you who are not here before, I run a company called Invoke RE and we do malware analysis training and services. And the reason I can do these free streams and do all this educational content is because we run these courses. So if you're interested in learning how to do malware analysis, definitely check us out there. So I'm just going to run a quick ad for our course and then I'll be right back and we can try this on more malware samples. So 2 seconds. Hey everyone, my name is Joshua Reynolds and welcome to the Invoke RE Introduction to Malware Binary Triage course. Throughout this course, you will learn to triage and reverse engineer malware binaries using a number of proven techniques. These include static analysis, which is the concept of analyzing malware at rest, and dynamic analysis, which is the concept of analyzing malware as it executes. We will also be analyzing network protocols used in malware command and control communications, malware obfuscation, packers and how to unpack them, process injection, how to write effective Yara rules to detect malware variants, and how to compare malware samples at a binary level. This course consists of 11 modules, each containing lectures and practical labs to apply knowledge that you have gained as you complete the course. We provide both video and written materials, so no matter what your learning style is, you can complete the course successfully. Thank you for checking out the course, and we look forward to teaching you. We will also be analyzing network protocols used in malware command and control communications, malware obfuscation, packers and how to unpack them, process injection, how to write effective Yara rules to detect malware variants, and how to compare malware samples at a binary level. This course consists of 11 modules, each containing lectures and practical labs to apply knowledge that you have gained as you complete the course. We provide both video and written materials, so no matter what your learning style is, you can complete the course successfully. Thank you for checking out the course, and we look forward to teaching you. All right. How's everybody doing? Okay, so I figured we could try Unpack Me for getting some more DCRat samples. So we can write a quick Yara rule, search across Unpack Me for those samples, and then see if our little tool works on them. So for those of you who are not aware, Unpack Me is just this service run by Open Analysis, and they'll basically unpack given malware samples for you automatically. So they have this really nice Yara interface that I'm going to be using today to search across DCRat samples, or search for DCRat samples rather. So I'm just going to do DCRat. And then this is going to be our little interface here. And I'm just going to, I figured we could just probably look for that salt that was used to derive the key. So if we look back at our VM here, then the salt that was used is this guy here. And that's pretty unique. So I feel like we can just search on that and we'll get a bunch of good results back. So let's do that. We'll just say Josh Reynolds and DCRat example to test. Okay. And then let's validate that and we'll save it. And then this is basically going to look in their sample set for the past 12 weeks, I believe. So I'm going to do a hunt. And actually, before I do this, I just want to make sure that it'll work locally. So let me copy this. And I'll just copy this Yara rule locally to make sure that it's working. So dcrat.yara. And then we'll run it against this sample here. Okay, so it did not match. So I think it might be wide. Okay, yeah, so I'm glad I checked that. So basically it's just a wide string instead of a normal ASCII string. So it's good that I checked. And then let's run that against our unpack me instance here. And then we'll do validate again, save, and then hunt. And then we don't need scripts. We can do labeled and unlabeled. And let's do launch. And then let's see what kind of results we get back. There should be a whole bunch of samples, hopefully. Wide 16, yeah. Yeah, it's just Windows. Being Windows, they always do this. Okay, cool. So we got a whole bunch of different samples back. They have them labeled as DCRat, but if I download one of these guys now, we can test with this. Okay, and I'm just going to move that over to my VM. Okay, and then let's go back to my VM here. DCRat other, put it here. This is kind of convoluted, but I just didn't log in on my VM. I probably should have just done that. Okay, so then if we run our tool against this, then we get good results here. So it looks like this domain, which submission gl atply.gg, super long domain name, but they're using port 59415, and then all of the rest of the results here. So it looks like our automation works against multiple DCRat samples, which is pretty cool. So the last thing I wanted to look at is, yeah, bingo. We can look at some other implementations here. So if I go to my AssemblyLine instance, I might have to log back in here, but I'll just grab a password real quick and then log in. And hopefully it's not too slow. My little machine downstairs is being slow. I might have to restart some of these services because it was being slow this morning. And if not, we can just look up another instance of this. Okay, AssemblyLine is working. It's just being crazy slow. Okay, so if I upload this other sample to the AssemblyLine, okay, so this should work the same way. So let's see how long this takes. Okay, so so this basically does the same thing. So it extracts the configuration. And this is kind of what I meant earlier with the different variants of DCRat. So like the XWorm config extractor worked, the KazarRat one worked, the DCRat one worked, the RKP Mako one worked. So like, I feel like these are all derivatives from the same malware variant. And then it labels all of them for us. It's pretty nice. So yeah, you should definitely check out AssemblyLine. It's like a free open source project. Yeah, so that's basically it. Anybody have any questions? Happy to answer some if y'all want to hang out. If not, I'll probably wrap it up. All right, thanks so much everybody for hanging out. Definitely check us out if you're interested in malware analysis. If I don't talk to you, let me get a link to the Discord in case y'all want to hop in and hang out. So yeah, there's a Discord invite link there. If you want to hop in, hang out, you can talk to me, you can talk to everybody else, you can work on these malware samples. yeah, really appreciate everybody sticking around till the end. Cheers.